This video will look at calculating the force on a current carrying wire. So the background to this, it comes in the electromagnetism course unit, part of the GCSE. And for this, we've got to understand magnetic field lines on permanent magnets and electromagnets, and have the knowledge of Fleming's left-hand rule. And you can see from this image just here, we've got some bar magnets, permanent magnets, with red and blue. And you should know which one is north and south. So the north one is the red one, and the south is going to be the blue one. And we should know that the magnetic field lines go from, have a little think, which direction? They go from north to south. Now I'm just doing them dotted lines here. Well, actually, let's do them full. There should be full lines. The key about magnetic field lines is that they do not cross at any point, and they need an arrow on. Just don't want to get confused with the wire going around it. And we've got a current carrying wire here. It's fully connected. We've got this bit here. And what do we call that? It's a cell, not a battery. Remember, a battery is numerous cells made up. And this side of the cell, this side of the cell is positive, and that side is going to be negative. And so with the current going round, it's going to go from positive to negative. So it's going to go in this direction here. So using Fleming's left-hand rule, you need to get your first finger pointing in this direction. Right, so your finger, if that's your finger there, needs to be, there's your fingernail, going in that direction there. And your middle finger, or your swearing finger, right, needs to go in this direction there. And if you do that, your thumb, all right, is pointing in the direction of the force of the wire. And if you're doing it correctly, it should be pointing up. Now we can calculate the force on that wire by using the F BIL calculation. Now I've got videos on my account that will go through Fleming's left-hand rule. And remember, you can remember it by using the idea of F BI. F is the thumb, that's going to be the force. I is current. B is the magnetic flux for your first finger, and I, your middle finger, is the current. So we can look at the force by doing this calculation. So we've got force measured in newtons. We've got B, and B might be new to you coming through here, and that is the magnetic flux density. So the magnetic flux density, and we measure that in Tesla. And then we've got I, which you should know is the current from the electricity topic at least, measured in amps. And then L is the length of wire, and we measure that in meters. So if we look at our diagram here, what we've got, we want to calculate this force. So to do that, we need to know the magnetic flux, all right, from those magnets there. We need to know the current from the potential difference, and also the length of the wire. So using once we've got those, we can quite easily calculate the magnetic force. Now, bearing in mind when we do this, a couple of key factors are there may be a conversion needed, because that's going to be in meters, but quite often that comes out in centimeters. So let's say we had it at 30 centimeters. We need to convert that to meters, which will be 0.3 meters. So there might be something similar to that in the exam. And remember, this will only work if, as well, our current carrying wire is perpendicular to the magnetic field generated by the permanent magnets. You might also be expected to rearrange the calculation here to work out maybe the magnetic flux if you know the force on there, So B is going to be equal to the force divided by current times the length of the wire. You can also calculate similar here, the current, that's going to be equal to the force divided by the flux times the length of the wire, and you can calculate the length of the wire by the force divided by the magnetic flux times the current. Now, if we look at this calculation again, we've got the magnetic flux, which we said is going to be measured in Tesla. So 1 Tesla can be also written as number of newtons, because that's force divided by the current, which is amp meters. Now, let's just go through one example. We've rearranged those. So we've got let's say we've got a 3 amp current going through with a magnetic flux or magnetic field of 0.1 Tesla, and the length of wire is 1 meter. So all you have to do to work out the force is to times them together. Give it a go, a nice easy one. I hope that helps you understand a bit more about how we calculate the force on a current carrying wire.